Howdy and welcome back. So let's get into class templates in C++. So class templates. Classes can also be parameterized like function templates by one or more types. What we're going to see here is that container classes such as vector and others are a typical example of this feature. And essentially what we can do is leave the element type that the container is going to store open as a template parameter. Now we'll see here that we can parameterize our types by types and also integer values. The kind of hallmark of this class template is going to be the header that we saw with respect to function templates. This declaration that tells the compiler that what's to come is going to be a template. In this case, it is going to be a class template. We can see here one template parameter. Class is effectively equivalent to writing type name, which we will prefer in this course to class. And then also, if we notice here in our list of template parameters, we can see that there's also the possibility of having an integer parameter if we'd like. Notice here that this is the class definition. So we have a class template. Notice that for our member function definitions, and assuming that push is a member of our stack, we also need to declare our members as function templates. And we'll get into a more concrete example here in a second. The reason being is that the member who we're defining this function for is going to be of the type, in this case, stack T and N, right here. Just like with function templates, for every type of stack that we're going to generate, if it's, say, from our template code, if it's stack int, that will be one type which will have its own set of member functions defined, or I guess instantiated for it. Those member functions will be different than those generated for, say, a stack of doubles. So to provide some exposure to class templates, let's go ahead and implement together a stack as a parameterized class. From this class template, we'll go ahead and kind of introduce how we could instantiate stacks that are specialized to hold elements of a specific type. For instance, and this is very reminiscent of what we did in our declarations for, say, a standard template library vector. Stack double that's a type in its own right. It was generated from our class template, and it will be used to create a stack of doubles. Stack int is a distinct type. It will be a stack whose elements are integer values. And then finally, in this case, we have a stack of pointers to characters. So this would be a stack of pointers to characters. And again, we could instantiate a stack for any type as long as that type supports all of the operations and behaviors that are within the member functions defined for this class template. If you remember, for our minimum value function, remember that was operator greater than, which needed to be supported by the types used to instantiate that function template. Here, we'll have a lot of other behaviors with potentially a lot of different operators presenting. In the type that we're using to instantiate a class or a type from our class template is going to have to support those operations. So definition of a class template. Before the class definition, so this is our class definition, if you recall. In order to declare a class template, we're going to have to declare one or more type parameters. T is going to conventionally be used as the identifier. So here we can see that keyword template again, which is announcing to the compiler that what's to come is a template from which we'll be able to derive types and to expect a single type argument upon the construction of a concrete stack. So in this case, the compiler is going to always kind of look for, okay, well, what is T? And we'll see for class templates, we're not going to have template argument deduction here. We're going to have to specifically state the argument that we're going to provide to initialize the type parameter T. So in this case, upon initialization, if you recall, it would go through and all instances of t would be converted to end. Now, one other important thing to note is that the use of the class name stack inside the class template is going to represent the instantiated class with its template parameters as arguments. So here, what this is really referring to, hold on, I'm having trouble connecting with my pen. This, oh, what's going on? Let me pause. Okay, we got it back. What this is referring to here, this return type of stack is going to be stack of t, where stack of t is going to be whatever type is used to initialize it, to instantiate this class template. So if it's stack end, that return type would be stack of end, because remember, each instantiation of a class template is going to create a new type. So a stack of int is a different type from a stack of doubles, which is a different type from a stack of pointers to characters to a stack of standard library strings. I think you can kind of see where I'm going with this. So yes, the type of the stack, type of the class is going to be stack t, where t is the template parameter. Therefore, this type must be used in all declarations where the template arguments cannot be deduced. When defining a member function outside of the class, we must provide stack t as the type in the fully qualified name. So in this case, we're saying push t of c belongs to stack for which it is instantiated for. So we would have, if we create a stack of int, we would have a stack of int push function created. If we had a stack of characters instantiated, a push would be created for that type. And for each type that were instantiated from our class template is going to get its own set of member functions. In this, when we're defining this member function, we have to communicate that to the compiler. So our member functions are always going to be declared and, defined as function templates, because we have to provide that t to the type name here. So in this case, template, type name t, and then we can use t in that fully qualified name to communicate that this member function definition is going to correspond to a particular instantiation of our class template. So using a class template. So I mean, this is very similar to our function templates that we've talked about before. By declaring stack of I, so if it's stack of int, stack of std character, string, etc. I, so in this case, enter standard library string, is going to be substituted for t everywhere it appears inside the class template definition, including its member functions. The process of replacing template parameters by these concrete types is called template instantiation. To instantiate a class template, again, you must specify the template arguments to the template parameters explicitly. Again, just to, get back into this, there is no template argument deduction here. Instead, anytime you're working with the stack, with the class template, so anytime you're going to say instantiate one, the arguments to the type parameters are always going to have to be explicitly noted. And we've done that here, we did that in the character example, the double example. There's no inference. So again, you must specify the template arguments to those template parameters explicitly. So let's go ahead and look at briefly look at a before and after for a stack. Let's say the first time through we implemented a stack of characters, and we want to go ahead and create a class template or derive a class template from this definition such that we can create stacks whose elements are of some sort of arbitrary type. So if we just begin looking through this, and this was, when I was at A&M, I given an exam question like this. For instance, do you understand a stack, and can you convert, say, a specialized stack into a class template? And what that requires you to do is kind of recognize how the behaviors operate as well as what the data members mean. So in this case, push, we're pushing a character member onto the stack, which means that if we're having a generic stack, that's probably going to be changed from character to some type T. Likewise for pop, if that is removing from the stack, well, likewise, if we're removing that character from the stack and we're now going to this generic kind of definition of a stack, well, that should be, of type T too, because the return type, or in this case, the type of element that is being removed is going to have to match with the type of element contained within this. And then obviously here, okay, we have a character. And again, this is just kind of looking at this definition. Our array here is residing on the stack. For the most part, you'd want to use, put that on the free store so that we have a resize capability. But here, just, we're showing a different way. So let's go with it. So this, the type of element that our array is going to store. In the specialized version, that's a character. In a generic version, would be an element of type T for whatever type the stack's being instantiated for. Now, a couple things to note. The fun thing to do on an exam is provide a stack of integers and then also denote the size or the top as an integer as well. And one of the common mistakes students make is they go through and they just replace every single instance of int to T. And you can't do that. You have to understand what each behavior is doing, what each data member is storing. Something like size or top, denoting the top element, should stay an integer when we go ahead and translate this concrete definition into a more generic form. So notice here, we had our class definition over in the header file. Our definition of the member functions for stack in our before class templates resided in the corresponding source file. We can see the fully qualified name here. Push is being defined as a member of stack. We can see the implementation here of this function, likewise for pop. So cool. Let's go ahead and convert this into a generic form. So notice the first thing we did here is we made it very clear that the class definition to come is a template from which it will be defined for concrete types. So this line right here is telling the compiler, hey, the class definition you're about to see, it is going to be for a class template. And you should expect anytime this type or anytime we're instantiating from this template, a single type template parameter, and it is going to be it's going to be a type name parameter named T. So now we can see here that, okay, we've made the changes as I previously described. Instead of pushing a character element onto the stack, we are actually pushing some element of type T on. And again, what T is going to be and what T is actually going to become is going to be dependent on the type we're using to instantiate this class. And then, okay, pop's now going to return an element of T. Our array is going to maintain elements of type T. Now notice here, because this is a class template, not only does the class definition have to reside in the header file, but the definition for every single member function does as well. And again, we'll get into this in the next section, but it's because the compiler needs to see these definitions so that it can go ahead and derive the correct code when a template is being instantiated with the concrete type. But we can see, here, similarly, the updates we made to the parameter list of our member functions in their declarations has been reflected in their definitions, as has been the return type. So at this point, if we were to compile this, provided everything that needs to be in the header file is, which is all of this, everything shown on this slide, we'd be able to create stacks of integers, stacks of pretty much whatever type, as long as it supported the behaviors or excuse me, the operations, yeah, so the behaviors as well as the operators that are residing within the definitions of our member functions. So just to, keep going forward, if we were to declare a stack event and it hadn't already been declared, the compiler would go ahead and generate this code for us. Notice every instance of t has been replaced with the concrete type int. And again, the compiler is doing this for us. You're not responsible for this. The second you write stack of, say, int, give it a, I don't know, call it stack, this code is generated for you from the class template. Likewise, if you go ahead and say, I want a stack of characters. So I don't know, maybe you call it stack of C stack. Anyhow, if we hadn't already introduced this type, so if we hadn't already instantiated a stack of characters, the compiler would go ahead and generate this code for us, provided, again, that the type used in the instantiation is able to support all of the operations and behaviors that are presenting within the member function definitions. And with that, we've completed our introduction to class templates, and we're now going to get into the class templates and implications when it comes to separate compilation.